So here's a question that might keep physicists up at night, and it's one of those questions that, the deeper you go, the stranger and more unsettling it gets. What if the most successful theory in the history of science, the one that predicted the magnetic moment of the electron to 12 decimal places, the one that gave us lasers and semiconductors and everything your phone does, what if that theory also made the single worst prediction any scientific theory has ever produced? And not wrong by a little, not wrong by a factor of 2 or 10 or even a million, wrong by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros. To put that in perspective, the total number of atoms in the observable universe is roughly 10 to the 80. So this prediction isn't just off by more atoms than exist. It's off by a number so large that the number of atoms in the universe doesn't even begin to describe the scale of the error. And here's the thing that makes this truly unsettling. This isn't some fringe theory making this prediction. This isn't some back-of-the-envelope calculation by a crank with a whiteboard. This is quantum field theory, the crown jewel of modern physics, the most rigorously tested, most precisely confirmed scientific framework ever devised by the human mind, the framework that underlies everything we know about particles, forces, and the fundamental workings of nature. And when you ask it one particular question, a seemingly simple question about empty space, it gives you an answer that is, without exaggeration, the most wrong answer any rigorous scientific theory has ever produced. That question is, how much energy is in empty space? Just empty space. The void. The gap between things, the darkness between the stars, the silence between the atoms. How much energy is sitting there, in the nothing? It sounds like it should be a simple question, maybe even a trivial one. And for centuries, the answer seemed obvious. None. Empty space is empty. That's what makes it empty. End of story. But quantum mechanics changed everything, as it tends to do. And when physicists finally sat down and used their most powerful tools to calculate the answer, they got a number so absurdly, fantastically wrong that it has haunted theoretical physics for the better part of a century. And the reason this matters, the reason this isn't just some abstract mathematical embarrassment, is that the energy of empty space determines the fate of the entire universe. It shapes whether the cosmos expands forever or collapses back on itself. It governs whether galaxies form, whether stars ignite, whether you and I and everything we've ever known gets to exist at all. So when your best theory of nature gives you an answer that's off by 120 orders of magnitude on a question this fundamental, that's not just a mistake, that's a crisis. And it's a crisis that has been sitting at the heart of physics for decades, unsolved, staring back at some of the smartest people who have ever lived. Tonight, we're going to unravel this. We're going to figure out what the prediction actually is, why the theory makes it, why it's so spectacularly wrong, and what, if anything, anyone has come up with to fix it. And I'll tell you right now, this story doesn't have a neat ending. Not yet. But the journey through it is one of the most fascinating things in all of science. Let's start with something you can feel right now. The space around you. The air, sure, but imagine clearing the air away. Imagine pumping every molecule out of the room you're in, every atom, every particle. You create a perfect vacuum. Nothing there. Just emptiness. For most of human history, that was pretty much the end of the story. Empty space was empty. The ancient Greek atomists, Democritus, Leucippus, believed that reality was made of atoms and void. The atoms were the stuff, the substance, the thing that mattered. And the void was just the absence of atoms, the nothing between the somethings. It had no properties, no energy, no character. It was as close to pure non-existence as you could get while still being somewhere. Aristotle disagreed. He actually argued that a true vacuum couldn't exist at all. He thought nature would never allow it, that space always had to be filled with something. Nature abhors a vacuum, as the saying goes. For Aristotle, the very idea of emptiness was incoherent. Take everything away, and what you have left isn't nothing. It's impossible. This debate went back and forth for centuries. But by the time Newton came along in the 1600s, the prevailing idea was that space was a kind of stage, a fixed, silent, passive backdrop where the real action, matter, forces, motion, played out. Space itself didn't do anything. It was just there, a container for the universe. Newton called it absolute space, an infinite, unchanging arena that existed whether or not anything was in it. And in the 19th century, physicists added something to this picture: the luminiferous ether. They thought space was filled with a subtle, invisible medium through which light waves propagated, the way sound waves propagate through air. But when Albert Michelson and Edward Morley ran their famous experiment in 1887, trying to detect the Earth's motion through the ether, they found nothing. No ether wind, no evidence of this invisible medium. The ether didn't exist. And eventually, Einstein's special relativity in 1905 explained why. Light doesn't need a medium. It propagates through empty space, just fine on its own. So by the early 20th century, empty space really was empty. No ether, no substance, just distance and duration. A passive stage for the drama of physics. And that intuition feels right, doesn't it? When you look at the space between you and the wall, or the gap between the Earth and the moon, it feels like nothing is happening there. It's just distance, just emptiness. The air might be doing something, sure, but the space itself? Inert, passive, silent. But it turns out that intuition is completely wrong. Spectacularly, beautifully, profoundly wrong. And figuring out why it's wrong is where this whole story begins. The first cracks in the idea of truly empty space came from a place you might not expect: the study of heat and light. In the late 1800s, physicists were obsessed with something called blackbody radiation. That's the glow you get when you heat something up. Think of a piece of iron in a forge. At first it's dark. Then it starts to glow a dull red, then orange. Then, if you get it hot enough, white. Every object that has a temperature gives off this kind of radiation, and by the 1890s, physicists were trying to figure out the exact mathematical law that described it. How much light at each wavelength does a hot object emit? The problem was, when they used classical physics, the physics of Newton and Maxwell, to calculate this, they got a catastrophe. Not a metaphorical catastrophe, an actual, named catastrophe. It's called the ultraviolet catastrophe, and it's worth understanding because it foreshadows, in a spooky way, the much bigger catastrophe we're here to talk about. Classical physics predicted that a hot object should radiate infinite energy at short wavelengths, in the ultraviolet range and beyond. The calculation, done rigorously by Lord Rayleigh and James Jeans, was straightforward. It used perfectly respectable, well-established physics, and it gave a perfectly absurd answer: infinite energy, which is obviously physically impossible. You'd be destroyed by standing near a warm cup of tea. Everything warm would be a death ray. Your body, at 37 degrees Celsius, would be radiating infinite energy, which would be bad for you in ways I probably don't need to spell out. The math was right, the physics was well understood, and the answer was insane. Sound familiar? Keep that pattern in your mind, because we're going to see it again, at a much larger scale. And here's where Max Planck enters the story. Planck was a German physicist, meticulous, conservative, deeply uncomfortable with revolutionary ideas. He was about 42 years old in the year 1900, right at the turn of the century, and he'd been working on the blackbody radiation problem for years. He tried everything within the framework of classical physics. Nothing worked. The infinities wouldn't go away. And then, in what he later described as an act of desperation, he found a mathematical trick that made them vanish. He assumed that energy wasn't continuous, that it came in tiny, discrete packets. He called them quanta, and with that single assumption, the math worked perfectly. The predicted spectrum matched the observed spectrum exactly. Now, Planck himself wasn't entirely comfortable with what he'd done. He kind of treated it as a mathematical convenience, not necessarily a statement about how nature actually works. But then a young patent clerk in Bern, Switzerland, took Planck's idea seriously. Very seriously. In 1905, Albert Einstein published a paper arguing that light itself is quantized, that it actually comes in little packets of energy, which we now call photons. This wasn't just a mathematical trick anymore. This was a claim about reality. And it was radical enough that even other physicists thought it was too radical. But Einstein was right, and that paper, more than the relativity papers he published the same year, is what eventually won him the Nobel Prize. But here's the thing about quanta that matters for our story tonight. Once you accept that energy comes in discrete packets, once you accept that the world is fundamentally quantum, something very strange follows. You can never completely empty a space of energy, and the reason has to do with one of the most important principles in all of quantum mechanics, the uncertainty principle. Werner Heisenberg formulated this in 1927, and most people have heard some version of it. You can't simultaneously know both the exact position and the exact momentum of a particle. The more precisely you pin down one, the more the other becomes uncertain. But here's the version that matters for empty space. There's a similar relationship between energy and time. You can't know the exact energy of a system over an arbitrarily short span of time. The shorter the time interval you look at, the more uncertain the energy becomes. And this means something profound about empty space. If you could truly have a region of space with exactly zero energy, absolute nothing, then you'd be specifying the energy with perfect precision, forever. And quantum mechanics says you can't do that. The uncertainty principle won't allow it. So even in the most perfect vacuum possible, there must be some residual jittering of energy, some irreducible fuzz, some minimum baseline hum. This is called the zero-point energy. It's the energy that remains when you've removed absolutely everything you can remove, the energy of nothing. And it's not zero. Now, at this point, you might be thinking, okay, sure, there's some tiny quantum fuzz in empty space. How much could it really matter? And for a long time, physicists thought exactly that. The zero-point energy was there, mathematically, but it was this tiny, maybe even negligible thing. Just a curiosity. But then came the experiments that proved it was real. And the most famous one, the most beautiful, direct demonstration that empty space really does have energy, was proposed by a Dutch physicist named Hendrik Casimir in 1948. Casimir predicted something remarkable. Take two perfectly flat, uncharged metal plates. Put them very close together. We're talking millionths of a meter apart, in a perfect vacuum. Classical physics says nothing should happen. There's no charge, no matter, no force between them. They should just sit there. But Casimir calculated that quantum mechanics predicts a force. A tiny but real attraction between the plates. And the reason is the zero-point energy of empty space. See, in the vacuum outside the plates, all possible wavelengths of quantum fluctuations can exist. But between the plates, only certain wavelengths can fit, the ones whose wave patterns match the gap between the plates. Wavelengths that are too long get excluded, so there are more quantum fluctuations pushing on the plates from outside than from between them. The result is a net force pushing the plates together. It's like this. Imagine you're standing between two walls in a rainstorm, and the rain is coming from all directions. Outside the walls, rain hits you from every side equally. No net force. But between the walls, some of the rain can't get in because the walls block it. So more rain hits you from outside than from inside, and you get pushed inward. That's roughly the idea. And in 1997, Steve Lamoureux at the University of Washington measured the Casimir force directly. He used an incredibly sensitive torsion pendulum, a delicate balance that could detect forces 1 trillion times weaker than the weight of a grain of sand, and brought a gold-coated sphere very close to a flat gold-coated plate. And he measured a force, a tiny, unmistakable, real force. A force between two uncharged, inert pieces of metal separated by empty space. The result matched Casimir's prediction to within about 5%. Later experiments refined this even further. The zero-point energy of empty space is real. Measurably, experimentally, undeniably real. The vacuum pushes things around. Nothing exerts a force. Think about that. Two metal plates, sitting in empty space, with nothing between them, no air, no radiation, no particles of any kind, and they're being pushed together by the energy of nothingness. If that doesn't make you feel a little dizzy, a little off balance in the best possible way, I don't know what will. So that's our starting point. Empty space isn't empty. It has energy. Real, measurable, force-generating energy. And now comes the question that broke physics. The question that has been sitting at the foundations of our deepest theories for decades, unanswered, mocking some of the greatest minds of the 20th and 21st centuries. How much energy? To answer that, we need to go deeper into how modern physics describes empty space. And the framework we need is quantum field theory, QFT for short. This is the big one. This is the theory that combines quantum mechanics with special relativity, and it's the foundation of the standard model of particle physics, which describes every known fundamental particle and 3 of the 4 fundamental forces of nature. In quantum field theory, the universe isn't really made of particles, not in the way you might think. The fundamental ingredients of reality are fields, quantum fields that permeate all of space. There's an electron field that fills the entire universe. There's a photon field. There's a quark field. For every type of particle, there's a corresponding field that extends everywhere. And what we call a particle is just an excitation of its field, a localized ripple, a vibration. An electron isn't a little ball flying through space. It's a vibration in the electron field. A photon is a vibration in the electromagnetic field, and so on, for every particle we've ever discovered. Think of it like the surface of a still pond. The pond is the field. It exists everywhere, calm or not. A particle is a ripple on the surface, a localized disturbance that propagates outward. No ripple, and the pond is in its ground state, its lowest energy state. But even a calm pond isn't perfectly still. At the quantum level, there are always tiny fluctuations, little jitters on the surface. Random, momentary disturbances that appear and vanish. And those jitters, that's the zero-point energy of the field. Now, physicists have a colorful name for these fluctuations. They call them virtual particles. And I want to be careful here, because the term is both useful and deeply misleading. Virtual particles are not particles in the way you'd normally think of them. They're not little balls popping in and out of existence. They're mathematical descriptions of the fluctuations in quantum fields, shorthand for the fact that the vacuum is constantly, restlessly doing things. When physicists draw Feynman diagrams, those beautiful, deceptively simple pictures that Richard Feynman invented to keep track of calculations in quantum field theory, the internal lines in those diagrams represent virtual particles. A photon is emitted by one electron and absorbed by another. The photon in the middle is virtual. It's not a real photon you could detect with a camera. It's a mathematical description of the electromagnetic interaction between the two electrons. But even though virtual particles aren't real in the everyday sense, their effects are. The Casimir force is real. The Lamb shift, a tiny shift in the energy levels of hydrogen atoms caused by the interaction of the electron with virtual photons, is real, and was measured by Willis Lamb in 1947 to stunning precision. The anomalous magnetic moment of the electron, a tiny deviation from the value predicted by basic quantum mechanics, caused by the electron interacting with the swarm of virtual particles around it, agrees with experiment to more than 10 decimal places. These are real, measured effects, produced by the quantum fluctuations of the vacuum. So the vacuum is alive. It's buzzing, it's dynamic, and it has energy. Now, here's where the trouble begins. In quantum field theory, every field has this zero-point energy. Every possible wavelength, every possible mode of vibration contributes a little bit of energy to the vacuum. And there are a lot of modes. In principle, you can have shorter and shorter wavelengths, all the way down. There's no natural cutoff. And when you add up all the contributions, all the zero-point energies from all the possible modes of all the fields in nature, you get infinity. That's not a metaphor. The naive calculation gives you a literally infinite energy density for empty space, which is obviously nonsense. So physicists do something reasonable. They impose a cutoff. They say, look, we don't trust our theory below a certain length scale. At some point, presumably at the Planck scale, which is about 10 to the minus 35 meters, our theory must break down because we don't have a working theory of quantum gravity. So let's only add up the contributions from wavelengths larger than the Planck length. Let's cut the sum off there. And when you do that, when you use the Planck scale as your cutoff, which is the most natural and physically motivated choice, you get a number. Not infinity anymore. A finite number, but that number is enormous. The predicted energy density of empty space comes out to roughly 10 to the 93 grams per cubic centimeter, or, in the units physicists prefer, about 10 to the 76 giga-electron volts to the fourth power. Let that sink in for a moment. According to the most natural interpretation of our best theory, every cubic centimeter of empty space should contain about 10 to the 93 grams of energy. That's more energy in a sugar cube-sized region of vacuum than in the entire observable universe, by a lot. And now, let's compare that to what we actually observe. We can measure the energy density of empty space. We know this because of one of the most stunning discoveries in the history of astronomy. The discovery, in 1998, that the expansion of the universe is accelerating. But let me back up a bit, because to understand why that discovery matters, you need to understand the story of the cosmological constant. And that story starts, as so many stories in modern physics do, with Einstein. When Einstein developed general relativity in 1915, he gave us a completely new way of understanding gravity. Gravity isn't a force pulling objects together, the way Newton described it. Gravity is the curvature of space-time itself. Mass and energy tell space-time how to curve, and the curvature of space-time tells matter how to move. It's one of the most beautiful ideas in the history of human thought. But when Einstein applied his equations to the universe as a whole, when he tried to figure out what general relativity says about the cosmos, he ran into a problem. And it's a problem that tells you something wonderful about how science works. Because the issue wasn't with the math. The math was flawless. The problem was with Einstein's assumptions about the universe. His equations naturally predicted a universe that was either expanding or contracting. The mathematics was clear. A static universe filled with matter is unstable. It's like a ball balanced on the tip of a pencil. Any tiny perturbation, and it starts to move. Gravity pulls everything together, so a universe filled with matter should be collapsing under its own weight. Or, if it started with some outward motion, it should be expanding. But it shouldn't just sit there, motionless. And in 1917, when Einstein did this calculation, everybody believed the universe was static, eternal, unchanging. That was just the assumption. The night sky had looked the same for all of recorded history. The stars appeared fixed. The idea that the universe itself was changing, expanding or contracting as a whole, was so far outside the conventional wisdom that it didn't even occur to most people as a possibility. So Einstein did something he later regretted. He added a term to his equations, a mathematical constant, a fudge factor, that would counteract gravity and keep the universe static. He called it the cosmological constant, and he gave it the Greek letter lambda. Lambda represented a kind of energy inherent to space itself, a repulsive effect that would exactly balance gravity and keep everything still. It worked mathematically, but it was, by Einstein's own admission, ad hoc. He put it there because he needed it, not because the theory demanded it. And then, about a decade later, everything changed. Actually, the first crack in the static universe came not from Hubble, but from a Belgian priest and physicist named Georges Lemaitre. In 1927, Lemaitre independently derived the expanding universe from Einstein's equations, and even connected it to observations showing that galaxies were receding. He published his results in a French-language Belgian journal, and almost nobody noticed. When Lemaitre showed his work to Einstein at a conference, Einstein reportedly told him, "Your calculations are correct, but your physics is abominable." Einstein simply couldn't accept an expanding universe. He was too attached to the static picture. But then came Edwin Hubble, working with the magnificent 100-inch Hooker telescope at Mount Wilson Observatory in California. At the time the most powerful telescope in the world, Hubble made observations that would reshape our understanding of the cosmos forever. First, in the early 1920s, he proved that the fuzzy nebulae that astronomers had been arguing about were actually entire galaxies, vast collections of stars far beyond our own Milky Way. The universe was suddenly much, much bigger than anyone had imagined. And then, building on earlier work by Vesto Slipher, who had measured the velocities of galaxies using the Doppler shift of their light, Hubble found something astonishing. Distant galaxies are moving away from us, and not just moving away. The farther away a galaxy is, the faster it's receding. This relationship, velocity proportional to distance, is now called Hubble's law, and it means the universe is expanding. This was shattering. The static universe that everyone assumed was wrong. And Einstein's cosmological constant, the thing he'd invented to keep the universe still, was unnecessary. At least, that's what everyone thought. Einstein reportedly called the cosmological constant his biggest blunder. He took it out of the equations, and for about 70 years, most physicists treated lambda as zero. Just set it to 0 and move on. But here's the thing about physics. Abandoned ideas have a way of coming back. And the cosmological constant came roaring back in 1998. That year, 2 independent teams of astronomers were studying distant supernovae, specifically a type called Type Ia supernovae, which are incredibly useful because they all explode with roughly the same brightness. That makes them what astronomers call standard candles. If you know how bright something actually is, and you measure how bright it appears, you can figure out how far away it is. It's like seeing a candle in the distance. If you know all candles produce the same amount of light, a dimmer candle must be farther away. One team was the Supernova Cosmology Project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory. Perlmutter had been working on this project since the late 1980s, nearly a decade of painstaking work, developing the techniques to find and measure distant supernovae. The other team was the High Z's Supernova Search Team, led by Brian Schmidt at the Australian National University, with a young postdoc named Adam Rees, doing much of the crucial data analysis. Both teams were trying to answer the same fundamental question: how has the expansion of the universe changed over time? The expectation was clear. Gravity is attractive. All the matter in the universe pulls on all the other matter. So like a ball thrown upward, it starts fast, then slows down as gravity pulls it back. The expansion of the universe should be decelerating. The only question was how fast it was slowing down, and whether it would eventually stop and reverse. To measure this, you need to look at very distant objects and figure out 2 things: how far away they are, and how fast the universe was expanding when the light left them. Comparing these 2 measurements at different distances, and therefore different times in cosmic history, tells you how the expansion rate has changed. That's where the Type 1a supernovae come in. These are exploding white dwarf stars, the dense remnants of dead stars, that detonate when they accumulate too much mass from a companion star. The physics of these explosions is remarkably consistent, which makes them almost identical in brightness. Each one is like a 100-watt light bulb. If you know the wattage, you can figure out how far away it is by measuring how bright it appears. Both teams spent years finding these supernovae in distant galaxies, carefully measuring their brightness and their redshifts, the stretching of their light due to the expansion of the universe. It was grueling, meticulous work. They had to account for dust, for variations in supernovae, for instrumental effects, for a dozen possible sources of error. But that's not what they found. The supernovae were dimmer than expected, farther away than they should have been if the expansion were slowing down. And the only explanation that fit the data was astonishing. The expansion of the universe isn't slowing down at all. It's speeding up. Something is pushing the universe apart, and that push is getting stronger over time. This was, and I don't use this word lightly, one of the most shocking discoveries in the history of science. Nobody expected it. The teams themselves didn't believe their own results at first. They spent months checking for errors, for systematic biases, for anything that could explain the data without invoking cosmic acceleration. They couldn't find anything. The universe is accelerating. And both teams announced their results independently, confirming each other. Perlmutter, Schmidt, and Rees won the Nobel Prize in Physics in 2011 for this discovery, and what they found brought Einstein's biggest blunder back from the dead. Because the simplest explanation for the accelerating expansion is that there is an energy inherent to space itself, a kind of pressure that pushes the universe to expand faster and faster. And that's exactly what the cosmological constant describes. Einstein's lambda, the thing he added and then removed. It turns out he might have been right to add it all along, just for completely different reasons than he thought. This energy of empty space, This mysterious stuff driving the acceleration was given a name. We call it dark energy, and it makes up roughly 68% of the total energy content of the universe. Let me say that again, because it's worth sitting with. More than 2/3 of everything in the universe, the vast majority of its energy, is this mysterious energy of empty space, and we have almost no idea what it is. Think about that pie chart of the universe that you might have seen. Ordinary matter, the stuff you and I and stars and planets are made of, makes up about 5%. 5%. Dark matter, which is mysterious stuff that has gravity but doesn't interact with light, makes up about 27%. And the remaining 68%? That's dark energy. The energy of nothing. We live in a universe whose dominant ingredient is something we cannot see, cannot touch, cannot produce in a lab, and cannot explain from first principles. We know it's there because of its gravitational effects. It makes the universe expand faster and faster. But beyond that, dark energy is one of the most profound mysteries in all of science. And the name itself, dark energy, is a confession of ignorance. It's not a name that tells you what the thing is. It's a name that tells you what we don't know. It's dark because we can't see it, and we call it energy because it acts like energy in the equations of general relativity. But the name is really just a placeholder, a label for our ignorance. But here's what we do know. We can measure how much dark energy there is. From the supernova observations, from measurements of the cosmic microwave background, the afterglow of the Big Bang, and from studies of the large-scale structure of the universe, we've pinned down the energy density of empty space to extraordinary precision. And the value is incredibly small. Expressed in the natural units of physics, the observed energy density of the vacuum is approximately 10 to the minus 47 giga-electron volts to the fourth power. So now, you have the two numbers, and you can see the catastrophe. The prediction from quantum field theory, using the Planck scale cutoff, roughly 10 to the 76 GeV to the fourth power. The observed value, roughly 10 to the minus 47 GeV to the fourth power. The ratio between them, 10 to the 123. Let's round it and call it 10 to the 120. That's the mismatch. That's the worst prediction in the history of physics. The theory overshoots reality by 120 orders of magnitude. To grasp how absurd this is, let me try an analogy. Say you're trying to predict the weight of a cat, and your theory tells you the cat weighs, let's see, 10 to the 120 times the actual weight of a cat. A typical cat weighs about 5 kilograms. Multiply that by 10 to the 120, and you get a number so large that it exceeds the mass of the observable universe by a factor of about 10 to the 67. Your theory predicted a cat that outweighs the entire cosmos by a factor that is itself an incomprehensibly huge number. That's how wrong this prediction is, and it's called the vacuum catastrophe, or, more formally, the cosmological constant problem. And it is, by common consensus among theoretical physicists, the most embarrassing, most profound, most stubbornly unsolved problem in fundamental physics. Let me pause here and make sure the scale of this error is really sinking in, because numbers this large can become abstract and lose their punch. Consider this: the most precise measurement in all of physics, the measurement that physicists are most proud of, is the anomalous magnetic moment of the electron. Theory and experiment agree to about 12 significant figures. That's like predicting the distance from New York to Los Angeles to within the width of a human hair. That's quantum field theory at its absolute best. And now the same theoretical framework, the same quantum field theory, applied to a different question, the energy of empty space, gives an answer that's wrong by 120 orders of magnitude. It's as if the same navigational system that can guide you to within a hair's width suddenly tells you that Los Angeles is located in a different galaxy, not a different state, not a different planet, a different galaxy, 120 orders of magnitude away from the right answer. The contrast between the theory's greatest triumph and its greatest failure is almost absurd, and both come from the same mathematics, the same physics, the same quantum fields. How can a theory be so spectacularly right about one thing and so catastrophically wrong about another? That question keeps physicists awake at night. Now, you might be thinking, okay, so the calculation gives a crazy answer. Can't you just, ignore it? Throw the prediction away and use the observed value? And yes, you can. That's essentially what physicists do in practice. You measure the cosmological constant. You plug the measured value into your equations, and everything works fine. The universe behaves exactly as general relativity predicts, with a small, positive cosmological constant. But that's not satisfying. That's not how physics is supposed to work. The whole point of a fundamental theory is to predict things from first principles. If your theory can't predict the energy of empty space, if it misses by 120 orders of magnitude, then something is deeply, fundamentally wrong with your understanding of either quantum fields or gravity or both. The vacuum catastrophe isn't just a wrong number. It's a signal, a distress flare from the foundations of physics, telling us that something about our picture of reality is missing. So let's dig into why the prediction goes so wrong. And to do that, we need to understand the calculation a bit more carefully. Remember, in quantum field theory, the vacuum, the state with no particles, still has energy because of the zero-point fluctuations of all the quantum fields. Every field is always jittering, and that jittering carries energy. The total vacuum energy is the sum of all these contributions. Now, here's one thing that makes this problem especially nasty. It's not just the zero-point energy that contributes. In the history of the universe, several important events happened that also added energy to the vacuum. These are called phase transitions, moments when the character of the vacuum itself changed. Think about water freezing into ice. Liquid water has a certain energy. When it freezes, it settles into a new, lower energy state, the crystalline structure of ice, and releases energy in the process. That's why you feel warmth when water freezes. It's giving up the energy difference between the liquid state and the solid state. Something similar happened in the early universe, but with quantum fields instead of water, and the energies involved were incomparably larger. The most important example for our purposes is the electroweak phase transition. In the very early universe, when things were unimaginably hot, the electromagnetic force and the weak nuclear force were unified. They were one single force. But as the universe cooled, somewhere around 10 to the minus 12 seconds after the Big Bang, these forces separated. The Higgs field settled into its current state, particles acquired mass, and the vacuum changed its character fundamentally. This phase transition released, or, more precisely, rearranged, a huge amount of energy, which contributes to the vacuum energy density. How much? The electroweak scale corresponds to energies of about 100 GeV, and the energy density associated with this phase transition is on the order of 100 to the fourth power. That's about 10 to the 8 GeV to the fourth, which is already 55 orders of magnitude larger than the observed vacuum energy. And there's another one, the QCD phase transition, related to the strong nuclear force, happened when quarks and gluons condensed into protons and neutrons. The energy scale there is about 200 MeV, which gives a contribution of about 10 to the minus 3 GeV to the fourth power, 44 orders of magnitude too big. So it's not just one contribution that's wrong. There are multiple, independent contributions to the vacuum energy, each from different physics, and each one is vastly larger than the observed value. For the final vacuum energy to be as small as what we observe, all of these enormous contributions, the zero-point energies, the electroweak condensate, the QCD condensate, and who knows what else from physics beyond the standard model, all of these contributions would have to cancel each other out to a precision of about 120 decimal places. Imagine writing down a number with 120 digits, and then writing down another number with 120 digits, and having them cancel so perfectly that only the last digit or two survive. That's the level of fine-tuning we're talking about. And there's no known reason in physics for this cancellation to happen. This is what makes the cosmological constant problem so devastating. It's not just that the prediction is wrong. It's that making the prediction right would require an almost miraculous cancellation between completely unrelated physical contributions with no known mechanism to produce it. It's like finding that the total weight of every fish in the ocean, plus the total weight of every grain of sand on every beach, plus the total weight of every star in the galaxy, all cancel out to leave exactly 3.2 grams. You'd look at that and say, that can't be a coincidence. There has to be a reason. But nobody can find one. Let me tell you about the people who've tried. One of the most natural approaches, the first thing a physicist might try, is to look for a symmetry that forces the vacuum energy to be zero. Symmetries are physicists' favorite tools. Many of the deepest truths in physics come from symmetries. Conservation of energy comes from the symmetry of time. Conservation of momentum comes from the symmetry of space. The deep structure of the forces of nature, electromagnetism, the weak force, the strong force, all emerge from symmetries called gauge symmetries. So maybe there's a symmetry that forces the vacuum energy to be zero. And in fact, there is one. It's called supersymmetry. Supersymmetry, or SUSY for short, is a theoretical framework that proposes a deep connection between the two basic types of particles in nature, bosons and fermions. Bosons are force-carrying particles, like photons and gluons. Fermions are matter particles, like electrons and quarks. In supersymmetry, every boson has a partner fermion, and every fermion has a partner boson. The electron has a partner called the selectron. The photon has a partner called the photino, and so on. Now, here's the key thing. In quantum field theory, bosons and fermions contribute to the vacuum energy with opposite signs. Bosonic fields add positive energy. Fermionic fields add negative energy. And in a perfectly supersymmetric universe, these contributions would cancel exactly, perfectly. Every bosonic contribution would be precisely offset by its fermionic partner. The total vacuum energy would be exactly zero. That's beautiful, right? Problem solved? Not quite. Because we don't live in a supersymmetric universe. If supersymmetry existed perfectly, every particle would have a partner with exactly the same mass. The selectron would weigh the same as the electron. The photino would be massless like the photon. And we would have detected these particles a long time ago. We haven't. No superpartners have ever been observed. The Large Hadron Collider at CERN, which smashes protons together at the highest energies ever achieved in a laboratory, has been looking for supersymmetric particles for years. Nothing. If supersymmetry exists at all, it must be a broken symmetry. The superpartners must be much heavier than the particles we know, which is why we haven't seen them. But if supersymmetry is broken, the cancellation is no longer perfect. the boson and fermion contributions no longer match exactly, and you get a leftover vacuum energy. How big is the leftover? It depends on the energy scale at which supersymmetry breaks, and for the energy scales we can probe, the energies the LHC can reach, the leftover is still enormously larger than the observed cosmological constant. You might reduce the problem from 120 orders of magnitude to, say, 60, which is progress, technically, but it's like saying your cat weight prediction is now only off by the mass of Jupiter instead of the mass of the universe. Still catastrophically wrong. So supersymmetry, at least as we currently understand it, doesn't solve the cosmological constant problem. It helps, maybe, depending on things we don't know, but it doesn't fix it. Let me tell you about another approach, and this one is more philosophical and more controversial. In 1987, the physicist Steven Weinberg, one of the great minds of 20th century physics, the man who helped unify electromagnetism and the weak force, and won the Nobel Prize for it, Weinberg published a paper with an extraordinary argument. He didn't try to calculate the cosmological constant from first principles. Instead, he asked a different kind of question. He asked, what values of the cosmological constant would be compatible with our existence? Here's the reasoning. If the cosmological constant were much, much larger than what we observe, if it were anywhere near what quantum field theory naively predicts, then the repulsive effect of dark energy would have torn the universe apart long before galaxies, stars, or planets could form. Matter would never have had the chance to clump together. No galaxies, no stars, no planets, no us. On the other hand, if the cosmological constant were large and negative, the universe would have collapsed back on itself almost immediately after the Big Bang. Again, no structures, no life. So if you want observers to exist, if you want beings like us, who can measure the cosmological constant and wonder about it, then the cosmological constant has to be incredibly small. Not exactly zero necessarily, but small enough that the universe can expand gently, form structures, and persist long enough for complexity to emerge. And Weinberg went further. He estimated what the upper bound should be if this anthropic reasoning were the whole explanation, and he got a number that was remarkably close to what was eventually observed in 1998, a full decade before the discovery. Weinberg essentially predicted the approximate magnitude of the cosmological constant, using nothing but the requirement that we exist to measure it. Now, this is simultaneously impressive and deeply unsatisfying. It's impressive because it sort of works. The observed value does fall within Weinberg's anthropic window. But it's unsatisfying because it's not really an explanation in the traditional physics sense. It doesn't tell you why the cosmological constant has the value it does. It just tells you that if it were very different, you wouldn't be around to ask the question. That feels less like a solution and more like giving up. And it gets more complicated when you bring in string theory. String theory is the most ambitious attempt in physics to unify all the forces of nature, including gravity, into a single mathematical framework. In string theory, the fundamental entities aren't point particles. They're tiny, vibrating strings of energy, and the different vibrational patterns correspond to different particles. It's a beautiful idea, and for a while, many physicists hoped that string theory would predict a unique set of physical laws, a unique vacuum state that would tell us why the constants of nature have the values they do. But that's not what happened. In the early 2000s, physicists realized that string theory doesn't have one vacuum state. It has an astronomical number of them. Estimates range from 10 to the 100 to 10 to the 500, a number so incomprehensibly vast that I can't even give you a useful analogy for it. Each of these vacuum states corresponds to a different possible universe, with different values for the constants of nature, including the cosmological constant. This vast collection of possibilities is called the string theory landscape. This was a shock to the string theory community. For years, the dream had been that string theory would predict one unique set of physical laws, the laws we observe. Instead, it predicted an almost incomprehensibly vast number of possibilities, with no obvious way to select among them. Some people called this the landscape problem, and saw it as a crisis for string theory. Others saw it as an opportunity. And here's where the anthropic argument and string theory combine into something provocative. If there are, say, 10 to the 500 possible universes in the string landscape, each with a different cosmological constant, then purely by chance, some of them will have a cosmological constant that's incredibly small as what we observe. And if there's some mechanism that actually realizes all of these possibilities, if all of these universes actually exist in some grand multiverse, then the anthropic argument tells you that we'd inevitably find ourselves in one of the rare universes where the cosmological constant is small enough for complexity and life to emerge. This is the multiverse explanation for the cosmological constant, and it's exactly as controversial as it sounds. Many physicists find it deeply troubling because it's not really testable. If the answer to why is the cosmological constant so small is because we're in one of the rare universes where it happens to be small, and in most universes it isn't, and those universes have no one in them to ask the question, well, that might be true. But it's the kind of answer that feels like the end of physics rather than its triumph. It's not a prediction. It's an after-the-fact rationalization. And a lot of physicists aren't ready to accept that. Let me tell you about some of the people who've pushed back. Paul Steinhardt, a theoretical physicist at Princeton, has been one of the most vocal and articulate critics of the multiverse approach. Steinhardt, ironically, was one of the original architects of inflationary cosmology, the theory that the universe underwent a period of exponential expansion in its first fraction of a second, and he's become disillusioned with where that theory has led. He argues that a theory that can explain anything, a theory that's compatible with essentially any value of the cosmological constant, any particle masses, any coupling constants, actually explains nothing. If string theory predicts 10 to the 500 possible universes, and you're just in whichever one you happen to be in, then the theory makes no testable predictions about the cosmological constant at all. And a theory that makes no predictions isn't science, Steinhardt argues. It's philosophy. Others have tried more concrete approaches. There's been a long search for what physicists call a degravitation mechanism, some process by which the vacuum energy simply doesn't couple to gravity. The idea is that maybe there's nothing wrong with the vacuum energy being large. Maybe the problem is that we're wrong about how vacuum energy affects space-time. Maybe vacuum energy gravitates differently than other forms of energy, or maybe some mechanism screens its gravitational effects on large scales. This is an appealing idea, but it's proven incredibly difficult to implement mathematically. General relativity treats all forms of energy democratically. They all curve space-time. To make vacuum energy an exception, you have to modify general relativity. And most modifications either break something else that we know is correct, or introduce new problems as bad as the one you were trying to solve. There's another approach worth mentioning, unimodular gravity. This is a modification of general relativity that's been around since the 1919, when Einstein himself explored a version of it. The idea is simple but subtle. In ordinary general relativity, the equations of gravity respond to the absolute value of the vacuum energy. Every bit of energy in the vacuum curves spacetime. But in unimodular gravity, you constrain the equations in a way that makes them insensitive to the overall level of the vacuum energy. Only changes in energy density affect the curvature of spacetime, not the absolute level. This sounds like it could solve the problem, doesn't it? If gravity doesn't care about the absolute vacuum energy, then it doesn't matter how large the quantum field theory prediction is. It simply doesn't gravitate. But here's the catch. In unimodular gravity, the cosmological constant reappears as an integration constant, a free parameter that you have to set by hand, using observations. So you haven't really explained why the cosmological constant is small. You've just moved the question from, why is the vacuum energy small, to, why is this integration constant small? It's a different way of parametrizing your ignorance, but it's still ignorance. Some physicists find unimodular gravity illuminating nevertheless, because it changes the nature of the problem. Instead of asking why the vacuum energy is small, which requires understanding all of particle physics, you're asking why a gravitational integration constant is small, which might be a simpler question. But as of now, it hasn't led to a breakthrough. There's another idea that's gained some attention, which comes from a different direction entirely. It's based on a concept called the sequester mechanism, proposed by physicists Nemanja Kaloper and Antonio Padilla around 2011. Their idea is subtle. Instead of trying to cancel the vacuum energy or make it not gravitate, they proposed a modification of how gravity couples to the vacuum at the level of the entire history of the universe. In their framework, the cosmological constant is determined dynamically. It's not a fixed input, but something that adjusts itself based on the global properties of spacetime. And remarkably, the mechanism automatically drives the effective cosmological constant towards small values, regardless of how large the individual contributions from particle physics are. It's clever, but it's not a complete solution. It requires certain assumptions about the structure of spacetime at very large scales, and it doesn't fully explain why the remaining cosmological constant has exactly the value we observe. It reduces the problem, maybe significantly, but it doesn't eliminate it, and that's a common theme in this story. Over and over, brilliant people come up with creative ideas that nibble at the problem, that reduce the severity of the mismatch, that offer tantalizing hints of a solution, but nobody has cracked it. Let me take you down another path, one that's more speculative, but reveals just how deep this rabbit hole goes. Some physicists have wondered whether the problem isn't with our theory of quantum fields, but with our theory of gravity. What if general relativity is wrong, or at least incomplete, in a way that's relevant to the cosmological constant? After all, we know general relativity isn't the final word on gravity. It breaks down at singularities, the centers of black holes, the very beginning of the Big Bang. It's fundamentally incompatible with quantum mechanics in these extreme regimes. We need a quantum theory of gravity to handle these situations, and we don't have one yet. Maybe, some argue, a proper quantum theory of gravity would naturally resolve the cosmological constant problem. Maybe the reason the vacuum energy doesn't gravitate the way we expect is that gravity works differently at the quantum level in some way we haven't figured out yet. And maybe the cosmological constant problem is actually the biggest clue we have to what quantum gravity looks like. This is the view of people working on approaches like loop quantum gravity, which is an alternative to string theory for quantizing gravity. In loop quantum gravity, space itself is quantized. It comes in discrete chunks, a kind of atomic structure of spacetime at the Planck scale. And some calculations in this framework suggest that the vacuum energy might be tamed by the discreteness of space, that the infinities that plague the quantum field theory calculation might not arise when you do the calculation properly in a quantum gravitational context. but loop quantum gravity is still a work in progress. The calculations are enormously difficult. The framework isn't complete, and there's no consensus on whether it actually solves the cosmological constant problem. It's promising, but then, many things have been promising in this field, and that brings up something worth talking about: the role of experiment. Physics is an empirical science. Ultimately, the cosmological constant problem will be resolved not just by theoretical brilliance, but by data, by observations, by measurements that tell us something new about the universe. And there's actually reason for cautious optimism on this front. Over the past 2 decades, our observational tools have become dramatically more powerful. The Planck satellite, launched by the European Space Agency in 2009, measured the cosmic microwave background, the oldest light in the universe, with unprecedented precision, and its results have confirmed and refined our measurement of the cosmological constant. More recently, large-scale galaxy surveys like the Dark Energy Survey and the Dark Energy Spectroscopic Instrument, DESI, have been mapping the 3-dimensional distribution of millions of galaxies, looking for subtle imprints of dark energy in the large-scale structure of the cosmos. These surveys can tell us whether dark energy is truly constant, or whether it's changing over time, which would distinguish between a cosmological constant and dynamical dark energy models like quintessence. And in fact, some recent results have been tantalizing. In 2024, the DESI collaboration released their first year of data, and their analysis suggested, tentatively, with significant caveats, that dark energy might not be perfectly constant. There were hints, at the edge of statistical significance, that the equation of state of dark energy might be evolving over cosmic time. If confirmed by future data, this would be enormous. It would rule out a simple cosmological constant and point towards something dynamical, something that might offer new clues to the vacuum energy puzzle. But we need to be careful. Hints are not discoveries. Statistical fluctuations can mimic signals. And the history of cosmology is littered with tantalizing results that evaporated under closer scrutiny. So we wait. We gather more data. We keep an open mind. The next generation of experiments, the Vera C. Rubin Observatory, the Euclid Space Telescope, the Nancy Grace Roman Space Telescope, will push our measurements to even greater precision. If dark energy is evolving, these instruments will see it, and if it's truly constant, they'll confirm that with extraordinary accuracy. Either way, the data will constrain the theoretical possibilities and, perhaps, point the way toward a solution. Let's talk about another angle, the possibility that the cosmological constant isn't actually constant. In the standard cosmological model, dark energy is described by a cosmological constant, a fixed energy density that doesn't change as the universe expands. Space expands, more space appears, and each new bit of space carries the same energy density. That's what makes the cosmological constant constant. But what if dark energy isn't constant? What if it changes over time, or varies from place to place? This idea is taken seriously, and models of dynamical dark energy, usually involving a hypothetical field called quintessence, have been extensively studied. In quintessence models, dark energy isn't a fixed property of space. Instead, it comes from a scalar field, similar in nature to the Higgs field, that fills the universe and slowly evolves over time. If the field is rolling very slowly down its potential energy landscape, it would mimic a cosmological constant to high precision, but the value of dark energy would actually be changing, just very gradually. This is interesting for the cosmological constant problem, because in quintessence models, the value of dark energy today isn't set by fundamental physics alone. It depends on the history of the field, on initial conditions, on how the field has evolved over billions of years. This opens up the possibility that the smallness of dark energy is not a fine-tuning problem, but a dynamical outcome. The field naturally evolves toward small values over the lifetime of the universe. But quintessence has its own problems. Why is the field rolling so slowly? What determines the shape of its potential? And the biggest question of all, even if quintessence explains the current value of dark energy, it doesn't explain why the zero-point energy from quantum fields doesn't gravitate. You still have to get rid of, or neutralize, the enormous vacuum energy predicted by quantum field theory before you can even begin to discuss whether dark energy is constant or dynamical. So the cosmological constant problem sits there, stubbornly, behind almost every attempt to understand dark energy. It's the foundation problem, the thing you have to deal with before anything else makes sense. Let me tell you about the person who first really framed this problem clearly, because his story is worth knowing. His name was Yakov Zeldovich, and he was one of the most remarkable physicists of the 20th century, though he's less well known in the West than he deserves to be, partly because he spent much of his career doing classified weapons work in the Soviet Union. Zeldovich was a self-taught polymath. He never earned a formal degree, but he made foundational contributions to nuclear physics, astrophysics, cosmology, and particle physics. He was one of the key figures in the Soviet hydrogen bomb program, alongside Andrei Sakharov, and in the late 1960s, Zeldovich turned his attention to the cosmological constant. In a series of papers starting around 1967, Zeldovich pointed out that the zero-point energy of quantum fields should contribute to the cosmological constant, and that the contribution was enormously too large. He was, as far as we know, the first person to clearly identify this as a serious problem. Before Zeldovich, most physicists either ignored the vacuum energy or assumed it could be set to zero by some convention. Zeldovich showed that you couldn't just ignore it. The energy was real, it should gravitate, and the predicted value was absurdly large. He also made the first crude attempt to estimate the size of the discrepancy, and while his initial estimates used different cutoffs and assumptions than what we'd use today, the essential point was clear. The predicted vacuum energy was too large by an enormous factor, and nobody had any idea why. It's fitting that this problem was first clearly articulated by someone who worked on nuclear weapons, because the vacuum catastrophe has something of the same character, an enormous, destructive energy lurking inside the most mundane-seeming thing. The difference is that the energy inside an atomic nucleus is real and can be released. The energy of the vacuum is real too, but somehow it doesn't do what our equations say it should. It just sits there, almost zero, defying everything we think we know. Here's something that I think is worth pausing on, because it reveals the real depth of this problem. The cosmological constant problem isn't just a conflict between one theory and experiment. It's a conflict between two of the most successful and well-tested theories in the history of science, quantum field theory and general relativity, at the precise point where they overlap. Quantum field theory tells you what the vacuum energy should be. General relativity tells you how that vacuum energy should affect the curvature of space-time, how it should make the universe expand. Both theories are spectacularly successful in their own domains. Quantum field theory predicts experimental results to extraordinary precision. General relativity predicts the orbits of planets, the bending of light around massive objects, the behavior of GPS satellites, and the existence of gravitational waves, all with remarkable accuracy. But when you combine them, when you take the vacuum energy predicted by quantum field theory and feed it into the equations of general relativity, you get an answer that's off by 120 orders of magnitude. It's as if two master craftsmen, each working perfectly in their own workshop, produce pieces that don't fit together at all when you try to assemble them. And this tells us something profound. The cosmological constant problem isn't a problem with quantum field theory alone, or with general relativity alone. It's a problem with the interface between them. It's a problem that lives in the gap, in the still unexplored territory where quantum mechanics and gravity meet. And that gap is exactly where the most fundamental mysteries of physics reside. This is connected, by the way, to another deep puzzle called the hierarchy problem, and it's worth spending a moment on because the connection illuminates both problems. The hierarchy problem asks, why is gravity so absurdly weak compared to the other forces of nature? Think about it this way. You can hold a refrigerator magnet against your fridge, and the tiny magnet, a little piece of iron, smaller than your thumb, holds itself up against the gravitational pull of the entire Earth. That's how weak gravity is compared to electromagnetism. Quantitatively, the electromagnetic force between two electrons is about 10 to the 36 times stronger than the gravitational force between them. 10 to the 36. That's a trillion. Now, in physics, when you see a number that's enormously far from 1, 10 to the 36, or 10 to the 120, it usually means you're missing something. There should be a reason, a mechanism, a symmetry, something that explains why these numbers are what they are. The hierarchy problem and the cosmological constant problem are like siblings. They're both about enormous, unexplained ratios. They both involve the relationship between quantum mechanics and gravity. They both resist every attempt at explanation. And some physicists suspect they might be related, that solving one might solve the other, or that both might require the same radical new ingredient. Here's a thought experiment that illustrates the depth of the hierarchy problem. Imagine you could turn a dial that controls the strength of gravity. If you turned it up by just a factor of 1 billion, which sounds like a lot but is tiny, compared to the factor of 10 to the 36, separating gravity from the other forces, then stars would burn through their fuel in a few million years instead of billions. There wouldn't be enough time for life to evolve. Planets would be crushed. The universe would be a very different place. The smallness of gravity, like the smallness of the cosmological constant, seems to be precisely calibrated for the existence of complexity and life. Whether that's a coincidence, a selection effect, or a clue to deeper physics, nobody knows. Let me take you back to the human side of this story for a moment, because I think the sociology of the cosmological constant problem is fascinating in its own right. For decades, roughly from the 1920s to the 1980s, most physicists simply assumed the cosmological constant was exactly zero. Not small, not fine-tuned, zero. And they assumed that someday someone would discover a deep symmetry or principle that explains why it's zero. This was the default position, and it was comfortable because zero is a natural number. Symmetries can naturally produce zeros. If the cosmological constant is zero, there's a plausible hope of a clean, elegant explanation. But then 1998 happened, and the cosmological constant turned out to not be zero. It's small, tiny in fact, compared to what particle physics predicts, but it's not zero, and that made the problem infinitely harder. Because now you don't just need a mechanism that drives the vacuum energy to zero. You need a mechanism that drives it to almost zero, but not quite, leaving just a tiny, positive residual that happens to become important at exactly the epoch in cosmic history when galaxies and stars and complex structures have already formed. Do you see how weird that is? The cosmological constant is so small that it was completely negligible for most of the universe's history. During the first 9 billion years or so, Dark energy was a rounding error. Matter and radiation dominated the cosmic budget. But right around the time that intelligent life emerged, right around now, cosmically speaking, dark energy became the dominant component. That timing feels suspicious. It's called the coincidence problem, and it's another layer of mystery on top of the magnitude problem. Why now? Why would the energy of empty space become important at roughly the same cosmic epoch when observers appear? Is that a coincidence? Or is it a clue? Let me put some numbers on this to show you how strange it is. The universe is about 13.8 billion years old. For the first roughly 9 billion years, matter dominated the energy budget of the cosmos. Dark energy was there, but it was a tiny fraction of the total, negligible. Then, around 4 to 5 billion years ago, dark energy started to catch up. And right about now, give or take a billion years, dark energy and matter are roughly comparable. Going forward, dark energy will dominate more, and matter will become negligible. So in the entire 13.8 billion year history of the universe, the epoch when dark energy and matter are comparable is a relatively narrow window, maybe a few billion years wide. And we happen to find ourselves right in the middle of it. Out of all the possible moments in cosmic history, we're in the one narrow epoch when the transition is happening. That's like throwing a dart at a timeline 13 billion years long and hitting a bullseye that's only a billion years wide. Not impossible, but suspicious enough to make you wonder if the dart was aimed. Some people, the anthropic reasoning camp, see this as further evidence for observer selection. Of course, we observe dark energy dominating now, they say, because now is when observers exist. In the far future, when dark energy has driven all galaxies apart and the universe is cold and empty, there will be no one around to notice. In the far past, when dark energy was negligible, there was no one around either. So of course we find ourselves at the transition point. Others are less satisfied with that argument and wonder if the coincidence is pointing towards some deeper dynamical connection between the energy of empty space and the emergence of cosmic structure. Maybe there's a feedback mechanism. Maybe the vacuum responds to the matter content of the universe in some way we don't understand. Maybe dark energy isn't just a spectator, but an active participant in the cosmic story, adjusting itself as the universe evolves. These are live questions. People are working on them right now, today, in universities and research institutes around the world, and they remain stubbornly open. Let me tell you about one more approach that's come up in recent years, because I think it illuminates just how creative physicists are getting in their desperation. It's based on a concept from information theory. Some physicists have proposed that the cosmological constant might be related to the information content of the universe, specifically to the holographic principle. The holographic principle, which emerged from the study of black holes in the 1990s, suggests that the amount of information that can be stored in a region of space is proportional not to the volume of the region, but to the area of its boundary. It's as if the three-dimensional universe is encoded on a two-dimensional surface, like a hologram. If you take this seriously, really seriously, then the maximum information content of the observable universe is determined by its boundary area, which is related to the cosmological horizon. And some calculations suggest that this maximum information content, when translated into energy density, gives a value that's in the right ballpark for the observed cosmological constant. Is this a coincidence, a clue, a genuine insight? Nobody knows. It's speculative. But it suggests that the cosmological constant problem might be connected to deep questions about the nature of information, entropy, and the structure of spacetime at the most fundamental level. And that's tantalizing. There's another recent line of thinking that I find particularly intriguing, and it has to do with the swampland program in string theory. The swampland is a name for the set of effective field theories that look consistent from a low-energy perspective, but can't actually arise from a consistent theory of quantum gravity. In other words, not every seemingly reasonable theory of particles and forces can be completed into a theory that includes gravity in a quantum mechanically consistent way. Some theories are in the landscape. They can arise from string theory or a consistent UV completion. Others are in the swampland. They look fine at low energies, but are fundamentally sick when you try to include gravity. And here's the remarkable thing. Some of the swampland conjectures, mathematical conditions that a theory must satisfy to not be in the swampland, have implications for the cosmological constant. One conjecture, called the de Sitter conjecture, suggests that a universe with a positive, stable cosmological constant might not be possible in a consistent theory of quantum gravity. If true, this would mean that our universe isn't actually in a stable state, that the dark energy we observe isn't a true cosmological constant, but something dynamical, something slowly changing, and that could, potentially, offer new ways into the cosmological constant problem. This is still highly controversial. Not everyone agrees with the de Sitter conjecture, and even among those who take it seriously, there's debate about its implications. But it shows you the kind of radical rethinking that physicists are willing to entertain when faced with a problem this stubborn. Let me bring us back to something more grounded for a moment, because there's an aspect of this problem that's easy to overlook but incredibly important. The cosmological constant problem isn't just a theoretical curiosity. It has real consequences for what we can predict and understand about the universe. Think about what it means for our models of the cosmos. The standard cosmological model, which we call lambda CDM, where lambda is the cosmological constant and CDM stands for cold dark matter, works beautifully. It fits observations of the cosmic microwave background, the distribution of galaxies, the expansion rate of the universe, and more. It's one of the great successes of modern science. But built into the foundation of that model is a number, the cosmological constant, that we can measure but cannot predict. We just put in the measured value and move on. And that's fine for practical purposes, but it means our deepest theory of the cosmos has a free parameter at its heart that we can't explain. It's like having a clock that keeps perfect time, but you can't explain why the gears are the sizes they are. The clock works. It tells you what time it is, but you have this nagging feeling that if you understood the gears, you'd understand something much deeper about the nature of time itself. The cosmological constant problem also intersects with one of the most profound questions in all of physics, the question of naturalness. Naturalness is a principle, maybe more of a guiding philosophy, that says the fundamental constants of nature should be of order 1 in natural units, unless there's a symmetry or mechanism that explains why they're small. A parameter that's unnaturally small, without explanation, is a sign that you're missing something. You haven't found the right description yet. By this criterion, the cosmological constant is the most unnatural parameter in all of physics. It's small, by 120 orders of magnitude, compared to its natural value. And the fact that we can't explain why has led some physicists to question whether naturalness itself is a reliable guide. Maybe the universe just is fine-tuned. Maybe some parameters are small for no deeper reason. Maybe we need to learn to live with that. But others resist. Nobel laureate Gerard Hooft, who gave us key insights into the renormalizability of gauge theories, has been a champion of naturalness as a guiding principle. His view, shared by many, is that a parameter as unnatural as the cosmological constant is practically screaming at us that we're missing a deep piece of the puzzle. The universe is trying to tell us something. We just haven't learned to listen. Think about what it felt like to physicists in the late 1800s, when the ultraviolet catastrophe was staring them down. Classical physics said hot objects should radiate infinite energy. That was clearly wrong, and the resolution, Planck's quanta, required a complete revolution in our understanding of nature, a whole new framework, quantum mechanics. Some physicists believe the cosmological constant problem is telling us something equally revolutionary, that the resolution won't come from a clever trick within our existing frameworks. It'll come from a fundamentally new way of thinking about space-time, quantum mechanics, gravity, or all three. And maybe that's the most honest and exciting thing about this problem. It's not just a puzzle to be solved. It's a signpost. It points toward the next revolution in physics. A revolution that hasn't happened yet, that we can't see the shape of, but that this problem, more than any other, is pushing us toward. Let's wander down one more path before we start winding toward the end. Because there's an aspect of this problem that touches on something almost philosophical, and I think it's worth spending a moment with. The cosmological constant problem forces us to confront a question about the vacuum, about empty space, that is surprisingly deep. What is the vacuum? What is the ground state of the universe? In classical physics, the vacuum is trivial. It's nothing. There's nothing to explain. But in quantum field theory, the vacuum is the most complex object in the entire theory. It's not nothing. It's a seething, structured, dynamic entity. It's the state of lowest energy, yes, but that state has an enormously rich structure. Virtual particles pop in and out of existence. Fields fluctuate. The vacuum has a non-trivial topology, a complicated energy landscape, and properties that depend on which phase of the theory you're in. And here's the thing. We've never really been able to look at the vacuum directly. We infer its properties from the particles and forces that emerge from it. We're like people, trying to understand the ocean by studying the fish, without ever being able to examine the water itself. We can study the ripples, the particles. We can study the currents, the forces. But the medium itself, the quantum vacuum from which everything arises, remains deeply mysterious. In some ways, the vacuum is the most important thing in physics. Everything we observe, every particle, every force, every structure in the cosmos, is a manifestation of the vacuum. Particles are excitations of the vacuum. Forces are interactions between those excitations, mediated by the vacuum. The entire material universe is the vacuum, excited. And yet, when we try to calculate the most basic property of the vacuum, its energy, we get the most wrong answer in the history of science. That should tell us something profound. It should tell us that whatever the vacuum is, our current description of it is incomplete in some fundamental way. The cosmological constant problem might be telling us that we don't understand the water, that our picture of the quantum vacuum, for all its successes, is fundamentally incomplete, that there's a deeper structure to empty space that our current theories can't see. And that's a strange and wonderful thought, isn't it? The space around you, the space between you and the walls, the space between the earth and the moon, this seemingly empty nothing might be the most mysterious thing in the universe. More mysterious than black holes, more mysterious than dark matter. The vacuum, the nothing, is where the deepest secret hides. Some physicists have even speculated that the universe might have started as pure vacuum, that everything, all the matter and energy and structure we see, crystallized out of the vacuum through phase transitions, like snowflakes forming from water vapor. In this picture, understanding the vacuum is understanding the origin of everything. And the cosmological constant problem is the central mystery of the vacuum. Let me tell you about one more beautiful connection that ties this whole story together. It has to do with the arrow of time. You're lying here, listening to this, and time is passing. It flows in one direction, from the past toward the future. That seems obvious, but it's actually one of the deepest puzzles in physics. The fundamental laws of nature, the equations of quantum mechanics, the equations of general relativity, are time-symmetric. They work the same way forward and backward. Nothing in the fundamental laws distinguishes the past from the future. So why does time have a direction? The standard answer involves entropy, the tendency of systems to evolve from ordered states to disordered states, as described by the second law of thermodynamics. But the second law raises its own question. Why did the universe start in such a low entropy state? Why was the early universe so orderly? And here's the connection to our story. The state of the vacuum, the cosmological constant, determines the long-term fate of the universe, and thus the ultimate structure of time. In a universe dominated by dark energy, as ours appears to be, the far future is a cold, empty, de Sitter space, a universe in thermal equilibrium at an incredibly low temperature. And the entropy of such a universe is related to the cosmological constant. A smaller cosmological constant means a larger cosmological horizon, which means a higher maximum entropy, which has implications for the arrow of time and the probability of our universe existing at all. Some researchers, particularly those inspired by the work of Roger Penrose, have tried to connect the cosmological constant to the problem of time's arrow, arguing that both problems might have a common origin in the initial conditions of the universe. Penrose himself has proposed a radical cosmological model called conformal cyclic cosmology, in which the far future of one cosmic epoch, when all matter has decayed and only radiation and dark energy remain, becomes, through a mathematical transformation, the Big Bang of the next epoch. In this picture, the cosmological constant isn't a problem to be solved, but a feature that enables the transition from one epoch to the next. It's wildly speculative, and most physicists are skeptical, but it exemplifies the kind of radical rethinking that the cosmological constant problem demands. The point is that the cosmological constant problem isn't isolated. It's woven into the fabric of the deepest questions about reality, the nature of time, the origin of entropy, the meaning of the vacuum, the structure of space-time at the smallest scales, the fate of the universe at the largest. It sits at the crossroads of everything we don't understand about fundamental physics. Let me tell you about a moment that captures the spirit of this problem beautifully. It involves Richard Feynman, one of the most brilliant and colorful physicists of the 20th century. Feynman was something special. Born in 1918 in Far Rockaway, New York, he had an intuitive, almost physical feel for physics that was unlike anyone else's. While other physicists approached problems through abstract mathematics, Feynman seemed to see the physics directly, as if he could watch the particles dancing and the fields vibrating in his mind's eye. He was one of the architects of quantum electrodynamics, QED, the quantum field theory of electromagnetism, which describes how light and matter interact. He developed the Feynman diagram technique, those deceptively simple pictures of particles interacting that revolutionized how calculations are done in particle physics. He won the Nobel Prize in 1965, shared with Julian Schwinger and Shinichiro Tomonaga, for this work. And he was famous for his ability to cut through nonsense and get to the heart of a problem. Feynman was well aware of the vacuum energy problem, and he had a characteristically direct way of describing it. He pointed out that in QED, the vacuum energy calculation gives you infinity, and physicists handle it by subtracting the infinity, a procedure called renormalization, which basically amounts to measuring the vacuum energy rather than calculating it. And this works perfectly for calculating everything else, the stuff you can measure, like the properties of particles and the outcomes of experiments. The infinities cancel when you compute differences. All the predictions of QED, those 12 decimal place agreements with experiment, come from computing differences between quantities, not absolute values. But the cosmological constant is an absolute value. It depends on the actual energy of the vacuum, not a difference. And that's the one thing the theory can't handle, the one thing you can't renormalize away. It's as if the theory is perfect at computing changes and relationships, but completely impotent when it comes to telling you the baseline, the 0 point, the sea level from which everything else is measured. And Feynman, in his characteristic way, essentially shrugged and said something like, "Well, we'll figure it out someday. In the meantime, we have bigger fish to fry." And for decades, that was the attitude. The cosmological constant was the elephant in the room that everyone acknowledged but nobody could do anything about. Wolfgang Pauli, another towering figure of 20th century physics, the man who discovered the exclusion principle that governs how electrons fill atomic shells, and who was famous for his devastating critiques of sloppy thinking. Pauli also wrestled with the vacuum energy problem. He reportedly calculated the vacuum energy using what he considered reasonable assumptions, and found that, if the vacuum energy were as large as the calculation suggested, the universe would be so severely curved that it couldn't extend beyond the distance from the Earth to the Moon. Since the universe very obviously extends far beyond that, something was clearly wrong. But Pauli, like Feynman, had no solution. He just noted the problem and moved on. There's something almost poignant about this. These were some of the greatest minds in the history of human civilization. Pauli, Feynman, Zeldovich, Weinberg, Dirac, and they all recognized the vacuum catastrophe, and none of them could solve it. Not even close. The problem humbled them all, and it continues to humble everyone who takes it seriously. But the fish have been fried. The bigger problems have been solved, or at least many of them have, and the elephant is still standing there. Bigger than ever, actually, now that we know the cosmological constant isn't 0. It's the last elephant, the biggest elephant, and it won't leave the room. Here's what I think is beautiful about all of this, and it's the thing I want to leave you with as we wind down. The fact that physics made the worst prediction in human history, that the most rigorous scientific framework we've ever constructed overshoots reality by 120 orders of magnitude. This isn't a failure of physics. It's actually a testament to how honest physics is as a discipline. Think about it. In most fields of human endeavor, when something goes wrong by a factor of 10 to the 120, you can hide it. You can sweep it under the rug. You can redefine your terms, move the goalposts, declare victory, and go home. But physics doesn't let you do that. The universe has a specific energy density of empty space. The theory predicts a specific value. The two disagree by a specific, quantifiable, undeniable amount. There's no way to pretend this isn't a problem. And physicists don't pretend. They've given this discrepancy a name, the vacuum catastrophe. They've called it the worst prediction in the history of physics. They've written hundreds of papers about it, held countless conferences, started careers trying to solve it, and ended careers without solving it. They've been honest about the fact that our deepest theories of nature have a gaping hole at their center, and they've been honest about the fact that nobody knows how to fix it. That honesty, That willingness to stare at an unfixable problem and keep working on it anyway is one of the most admirable things about the scientific enterprise, and it's why I'm optimistic, despite the apparent hopelessness. Physics has been here before. The ultraviolet catastrophe, the problem that launched quantum mechanics, was every bit as intractable in 1899 as the vacuum catastrophe is today. And the resolution was something nobody could have anticipated, an entirely new framework, a revolution in our understanding of nature. Maybe that's where we're headed. Maybe the cosmological constant problem is the loose thread that, when pulled, will unravel our current understanding and reveal something deeper, a new framework, a new way of thinking about space and time and energy and matter that we can't even imagine right now. Or maybe the universe really is fine-tuned. Maybe the cosmological constant is small for no deeper reason than that it has to be for us to exist. Maybe the multiverse is real, and we're in one of the rare hospitable patches, and that's just how it is. Or maybe the answer is something nobody has thought of yet. Something a graduate student somewhere is scribbling on a whiteboard right now, or thinking about while lying in bed, not sleeping, staring at the ceiling. That's what's amazing about being alive at this moment in the history of science. The deepest questions are still open. The most fundamental things about reality, the nature of space, the energy of emptiness, the origin of the cosmos, the fate of the universe, remain genuinely mysterious. We're not at the end of the story. We're in the middle, and the next chapter could come from anywhere. So let's come back to where we started. Empty space. The space around you, right now, in this room, wherever you are. It seems like nothing. It feels like nothing. But it's not nothing. It's a quantum vacuum, alive with fluctuations, buzzing with the zero-point energies of every field in nature. And those fluctuations carry energy, measurable, real energy, that shapes the expansion of the cosmos itself. How much energy? Quantum field theory says, an incomprehensible amount. The universe says, almost none. The gap between those two answers is the biggest unsolved problem in fundamental physics. A gap of 120 orders of magnitude. A gap so vast that it makes every other disagreement between theory and experiment in the history of science look like a rounding error. And nobody knows why. That's not a frustrating thing, if you think about it the right way. It's a beautiful thing. It means the universe still has secrets, deep ones. Secrets hidden in the most ordinary seeming thing imaginable. The emptiness right in front of your face. The space between you and the wall. The gap between the blanket and the ceiling. The quiet darkness all around you. It's not empty. It's a mystery. The greatest mystery in physics. And it's everywhere. It's the most common stuff in the universe. Emptiness. And it's the thing we understand least. There's something peaceful about that if you let it wash over you. The idea that the most familiar thing, the nothing, the space, the quiet, is also the most profound. That the simple act of being in a room, surrounded by empty space, puts you at the heart of the deepest question in all of science. You're immersed in the mystery, right now. It's all around you, and no one on Earth can explain it. The physicists are working on it. In offices and labs in Princeton and Cambridge and Tokyo and Geneva, people are thinking about this tonight, just like you're thinking about it right now. They're scribbling equations on whiteboards, running simulations, arguing over coffee, lying awake staring at the same ceiling you might be staring at. And someday, maybe, one of them will figure it out. Or maybe it'll be someone who hasn't been born yet. Or maybe the answer will come from a direction nobody expects, from a branch of mathematics, or from an experimental result at a collider that hasn't been built yet, or from a telescope that hasn't been pointed at the sky yet. But for now, the mystery is open. The vacuum hums with its unexplained energy. The universe expands, gently, into the darkness. And the worst prediction in the history of physics sits there, patient and unsolved, waiting for the person who will finally understand what empty space is trying to tell us. And you're lying here, in that space, surrounded by it, part of it. Every atom in your body is made of quantum fields, the same fields whose vacuum energy creates the problem. The electrons in your cells are excitations of the electron field. The quarks in your nuclei are excitations of the quark field. The photons from the lamp or the screen are excitations of the electromagnetic field. You are literally made of the stuff that generates the mystery. The vacuum catastrophe isn't something happening far away, in some abstract mathematical realm. It's happening in you, and around you, and through you, right now. The zero-point energy of the fields that make up your body is part of the vacuum energy that we can't explain. You are the mystery, as much as the space around you is, and that's a thought worth falling asleep to. The universe is mostly empty space, and that empty space is mostly unexplained. The thing we thought was simplest, nothing, turns out to be the most complicated. The thing we thought we understood, empty space, turns out to be the biggest puzzle. And the prediction we got most wrong, the energy of the vacuum, might just be the key to the next great revolution in our understanding of nature. But that revolution is for another day, for another mind, for another late night of scribbled equations and sudden insights, and the slow, patient, beautiful work of figuring out how the universe actually works. For now, it's enough to know that the mystery exists, that it's real, that it's all around you, and that it's one of the most wonderful things about being alive in this particular moment in the history of the cosmos, this brief window when we know enough to see the problem, but not yet enough to solve it, when the question is clear, but the answer is still hidden somewhere in the mathematics of the vacuum, waiting to be found. So let the emptiness settle around you. Let the silence fill the room, and know that in that silence, in that emptiness, there is more going on than anyone has yet been able to explain. The quantum fields are fluctuating. The vacuum is humming. Dark energy is doing its quiet, steady, mysterious work, pushing the universe gently, imperceptibly outward, into the endless night. And right here, in this small corner of a vast and largely empty cosmos, you're lying in bed, surrounded by the deepest mystery in all of physics. The worst prediction ever made, the most beautiful unsolved problem, the question mark at the heart of everything. Let it be a comfort, in a strange way. The universe is stranger than we know, emptier, and yet fuller, more mysterious, and yet more mathematically precise. A place where a single wrong number, 10 to the 120, might hold the key to everything we don't yet understand. There's a beautiful passage by the physicist John Archibald Wheeler, Einstein's last great collaborator, the man who coined the terms black hole and wormhole, where he describes his vision of physics at the deepest level. Wheeler imagined that at the Planck scale, space-time itself is not smooth but turbulent, a churning foam of quantum fluctuations, where space and time lose their ordinary meaning. He called it space-time foam, and he believed that the ultimate nature of reality, matter, energy, space, time, everything, would turn out to be information. It from bit, he said. Reality arises from information. If Wheeler was right, if the deepest level of reality is informational, not material, then maybe the cosmological constant problem is pointing us toward that deeper level. Maybe the vacuum energy is so hard to calculate because we're trying to compute it using the wrong language, the language of fields and particles and forces, when the real answer lies in the language of information, entropy, and the quantum structure of space-time itself. That's speculative, of course. But it's the kind of speculation that the cosmological constant problem invites. When a problem is this deep, this stubborn, this resistant to every clever idea that brilliant people have thrown at it, maybe it's not a problem to be solved within our current framework. Maybe it's a signpost pointing beyond it. A crack in the floor revealing a deeper basement that we haven't yet explored. And there's something reassuring about that. Not everything needs to be understood tonight. Not every mystery needs a solution before you fall asleep. Some mysteries are companions. They sit with you. They keep you company. And the vacuum catastrophe is the greatest companion mystery of all. Always there, in every cubic centimeter of the space around you, humming its quiet, inexplicable hum. You know, there's a wonderful tradition in physics of naming things after the emotions they evoke. The ultraviolet catastrophe, the measurement problem, the dark energy, the cosmic coincidence. Physics is full of poetry, even when, especially when, the poets don't know the ending of the story they're telling. The vacuum catastrophe is one of those poems. It starts with a simple question, how much energy is in nothing, and spirals outward into the deepest questions about reality, about what space is, what fields are, what gravity does, what the universe is made of, why there's something rather than nothing, and what nothing even means in a quantum world where even emptiness is alive. And you're part of this story, not just as a listener, but as a participant. The atoms in your body were forged in ancient stars. The protons in your cells have existed since the first microseconds after the Big Bang. The quantum fields that make up your being, the electron field, the quark field, the electromagnetic field, these are the same fields whose vacuum fluctuations create the problem. You are not separate from the mystery. You are an expression of it, a temporary, beautiful arrangement of quantum fields in a universe whose vacuum energy we cannot explain. Sleep well. The vacuum will keep humming. The universe will keep expanding. The dark energy will keep doing its quiet, patient work. And the mystery will still be here in the morning, profound and unsolved, waiting, as it has waited for decades, as it may wait for decades more, for someone to finally understand what empty space has been trying to say all along.